Hola, ¿cómo estás, scholars? In this video, I want to go over what you need to know about triangles for the test. This video will be quick and to the point, and won't go over basic triangle facts like finding the area or perimeter. Instead, this video will focus on the Pythagorean theorem and triples, similarity, and special right triangles. So buckle up, this is going to be a fast ride. First up, we have the Pythagorean theorem and the Pythagorean triples. I can bet you've seen this before, so I'll be quick about it. This only applies to right triangles, and what we're saying is if we are given two sides of a right triangle, we can always find the third side using this formula: a squared plus b squared equals c squared. But here's a part that you might not know. Did you know that the formula is literal? As in, if you turn side A into a square and also side B into a square, then add them together, they will literally sum up to the same units as side C? Now, the Pythagorean theorem is great and all, but I want you to try to not use it on the tests. Bet you didn't expect me to say that. Instead, I want you to keep in mind that the tests love certain types of right triangles, and more often than not, if you see a right triangle on the test, it will be a Pythagorean triple, meaning that it will follow the following ratios: 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. I'm going to need you to memorize these, for reals. If you memorize these, you may be able to solve a geometry problem in 10 seconds, as opposed to spending minutes using the Pythagorean theorem. Let's look at an example. Let's say we have this right triangle. And sure, you can plug everything into the Pythagorean theorem and take 2 minutes to solve it. Or you can look at it and realize that it's a 5, 12, 13 right triangle with a multiplier of 3. So the answer to x is just 13 times 3, or 39. Here's the key to how to check if it's a Pythagorean triple. Always look at the smallest side first to see if it's a ratio of one of the smaller sides of the Pythagorean triples. If it is, then find out what ratio it is and multiply that by the second number to see if you get the second side length. Next up, we have similar triangles. This is when triangles have the same angles but different lengths. Think of it like this. If an architect needed to build a scaled model of a building, then the miniature building would be similar to the actual building. Just the length and size would be different. We can even say that the ratio of the lengths are constant throughout the model building. You can even decide what ratio to build the building. We can decide that the model will be at a ratio of 1/100 of the actual building size, or 1/1000, or an itty-bitty 1/10,000 of the size. Take these triangles, for instance. We have the larger triangle ABC with angles XYZ. If we compare this to the smaller triangle, we see that the angles are the same, XYZ, but the lengths are now DEF. These are what's called similar triangles. By the way, remember this: if two triangles share at least two angles that are the same degree, then the third angle must be the same as well. Thus, the triangles are similar. In other words, you just need to match two angles and the triangles are similar. Another way to achieve a smaller triangle is to make an inscribed triangle within a right triangle. All you need to do is draw an altitude so that this new line is perpendicular to the opposite side. The two triangles within and the original triangle will be similar. The lengths of these similar triangles are directionally proportional. So, on the test, if you find out that two triangles are similar and had to figure out a missing side of the triangle, you would just need to set up a proportion. Let's try this problem together. If ADE is any triangle and BC is drawn parallel to DE, then the ratio AB over BD is equal to AC over CE, AB over AD is equal to AC over AE is equal to BC over DE. What is X? Okay, so the first thing to notice here is that the inscribed triangle is similar to the overall triangle. Side BC corresponds to side DE in a ratio of 3:6 or 1:2. Therefore, solving for X is easy now because we already know the ratio of the triangles. The only issue is we are given side BD as 4, which is not the full side of the triangle. But we know that x plus 4 must equal twice the length of x, or 2x. So let's set up that equation and solve for x. We can subtract x from one side to another, and we get x is equal 4. That's it! Also, if you were paying attention, did you also notice that this was a 3, 4, 5 right triangle? So if the smallest side is 3 and the corresponding side is 6, then the multiplier is 2, which means most likely side AD will equal 8. So we know x will equal 4. This would have taken 10 seconds to solve if you had memorized the Pythagorean triples already. Here, you try this one. A summer camp counselor wants to find a length, x, in feet across a lake as represented in the sketch above. The lengths represented by AB, EB, BD, and CD on the sketch were determined to be 1,800 feet, 1,400 feet, 700 feet, and 800 feet respectively. Segments AC and DE intersect at B, and angle AEB and angle CDB have the same measure. What is the value of x? Did you get it? The first thing we want to do is label the sides in the diagram. So AB is 1,800 feet, EB is 1,400 feet, BD is 700 feet, and CD is 800 feet. Now we need to see if the triangles are similar or not. We know that angle E and angle D are congruent per the problem. So we just need to match one more angle for them to be similar. How about the two angles of B? They would be congruent due to the vertical angle theorem. There we go! We've proven that the two triangles are similar. Now, all we need to do is set up a proportion. So, side X, or side AE, directly corresponds with side DC, which we know to be 800, and we know that EB and BD correspond with each other, and that is 1,400 to 700, or 2 to 1. Therefore, we just need to double side DC as well to get 1,600 for side AE. That's it! Okay, moving on to the last thing I'm going to show you in this video, special right triangles. These are the test's favorite type of triangles. Basically, they are right triangles that have angles that follow a certain ratio. 30, 60, 90, and 45, 45, 90. If you know that a right triangle fits this profile, then you can quickly calculate the lengths of the sides without the Pythagorean theorem, as they will always follow the same ratio of sides. Let's start with the 30, 60, 90 right triangle. The first thing to know about this right triangle is that it is half an equilateral triangle. This is important to remember in case you ever need to find the measurements of one. Our job is now to memorize the ratios of each side. Let's start with the smallest side, or the side opposite to the 30-degree angle. Since this is half of an equilateral triangle, we know that the smallest side must be half of the side opposite to the 90-degree angle or hypotenuse. That's easy enough, right? But what about the side opposite to the 60-degree angle? That side will always be the smallest side times the square root of 3. The important thing to remember here is that how you go about solving the different sides depends on what information you are given to start with. Earlier, we spoke about the 30, 60, 90 right triangle from the perspective of the smallest side. But what happens when you are given the hypotenuse first or the side opposite the 60 degrees? Let's continue with the hypotenuse. We remember that it is twice the size of the smaller side, so we would do the opposite to find the smaller side and divide it by 2. Then we know that the side opposite the 60-degree angle is the smaller side times the square root of 3. So it would be half the hypotenuse times square root of 3. Lastly, if you were given the length for the side opposite the 60-degree angle first, then the easiest way to memorize it is that you'll need to divide by the square root of 3 to get the smaller side. But remember, you can't just divide by a square root of 3, so we'll need to rationalize it. For a refresher on how to do this, see our video on radicals. Once we rationalize it, we find that all we need to do is multiply x by the square root of 3 over 3. Then, of course, for the hypotenuse, we just double the shortest side. Let's see this in action. If we have this 30, 60, 90 right triangle, and we are given the side opposite the 60 degrees, then we know side B will be 11 root 3, divided by root 3, which leaves 11. Then we know that side A is just double side B. So 11 times 2 is 22. And done. See how fast that was? No Pythagorean theorem needed. Okay, pause the video and try this one yourself. Did you get it? First, you should have recognized that it's a 30, 60, 90 right triangle and that they gave you the side opposite the 60-degree first, which means the smallest side is just 12 divided by root 3, or 12 times root 3 over 3. 12 over 3 comes out to be 4, and you're left with 4 times root 3 as the side length of y. Then, to find the hypotenuse, we just double it. So then, 2 times 4 root 3 is 8 root 3. And that's it. If you didn't get it right away, don't worry. With enough practice, it will become second nature. Now, let's move on to the next special right triangle, 45, 45, 90s. Another name for this is an isosceles right triangle because you have two angles that are the same. The second thing I want you to notice is that this type of triangle is just half of a square. Therefore, two sides will be the same, and the hypotenuse is just the diagonal of the square. So here, there are only two options for you to start with, either the side or the hypotenuse. Let's begin by starting with the side. If you start with the side, then the hypotenuse is just the side times the square root of 2. Every time, all the time. Super easy. Next, can you guess what to do if we start off with the hypotenuse? Exactly. We just divide by root 2. Or, after rationalizing, we multiply the hypotenuse by root 2 over 2. For example, let's say we have this 45, 45, 90 right triangle, and we are given one of the sides as 8. We automatically know the other side must be 8 as well. And the hypotenuse will be 8 times the square root of 2. Easy, right? Now you try this one. Go ahead and pause the video. Okay, for this 45, 45, 90 right triangle, you are given the hypotenuse of 10. We know to get the side lengths, we just multiply 10 by root 2 over 2. So 10 divided by 2 is 5, so you're left with 5 times root 2. Did you get it? Excellent! Okay, let's put it in a real-life word problem. Take a look at this example. Pause the video if you think you can solve it yourself. You're on a salvage ship in the Pacific Ocean when your ship's sonar locates a shipwreck at an angle of depression of 60 degrees, as shown in the figure below. After your ship travels 500 meters on the surface of the water to be directly over the wreck, how many meters down would you have to dive to reach the wreck? Here, the first thing that you'll notice is that it's a 30, 60, 90 right triangle problem. If I were you and I saw this on the test, I would start smiling because this is going to be easy. It looks like you're given the side opposite the 30 degrees as 500 meters. So, to find the side opposite the 60 degrees, what do? Multiply 500 by the square root of 3, of course. That comes out to be 500 root 3, which is the answer. 10-second problem. I hope you have a better understanding of triangles and can apply what you've learned to test problems. Be sure to memorize your Pythagorean triples and special right triangles. Have a wonderful rest of your day. Hasta luego!